Welcome to lecture 10. We will continue our discussion on hardness of approximations based on the Uniqueness conjecture. Today we will discuss vertex or the hardness of vertex curve, a reduction due to quote and regel. You can see a UG hardness of 2 minus epsilon approximating vertex. Reduction due to quote and regel. And quote and regel actually the paper have a short paper, but they have two important parts. They first modify UG to a form that's slightly more convenient than what we have seen. And the second part is the application towards vertex cover. So what I will do is we need both parts because they need that modification for this one. But I will actually not prove the steps in the modification. I'll tell you what the modification is. And that's a combinatorial modification. So let's recall from last time.
One vertex cover is different from the previous problems because it is not a CSP.
It's not a CSP. It's not a CSP. It's not a CSP. It's not a max CSP. So for max CSP, there's a subsequent result for all max CSP, UG hardness to Raghavendra, which we will not do. But vertex cover is a different problem. That's the reason. In fact, for looking at max cut and vertex cover, these are two different types of problems that we're looking at. So recall the ULC, the gap 1 minus epsilon delta ULC problem. What was it? The S square instances. So how was the instance? The instance was P, which is first a bipartite graph UVE. Then a label set and psi, which is the matching. You call this? We have called. What do you call sigma cross sigma 0? Rest, not functions, but even weaker than functions. What do you call anything of the forms? F cross sigma cross equal to 0, 1, 5. Yeah, it's a matching relation. Yeah. This is how we had stated it, and the val of I was the max over all labelings to the left side and the right side. But that probability when you pick an UVH psi UV of AU BB. That was how we can define it. And S instances where those P such that val phi was greater than or equal to 1 minus epsilon, and then no instances where those P for which val phi is less than or equal to that. And these were and the bipartiteness came because of the reason this was a bipartite graph was because historically label cover was a bipartite graph, and that was how we done it. Notice last time itself when we did the max cut, we actually went back, though we had it in the bipartite formulation, we actually did, the edges, we took edges of this form.
I had a question regarding this.
Sure.
I'll ask.
Okay. If it's max cut, let's do it after class. Yeah, so we had this one. So you might have actually just considered one side and put edges between two vertices. So you can not have a bipartite version of the graph, but a single, just to make things simpler, just have a regular graph. So we could move. So the fourth radius makes several modifications. First step is move to a unipart, what do you call it, non-bipartite setting. The phi is now just of the form G, B comma E. There is one label, and then there's once again one. The only thing this will do is move completeness from 1 minus delta to 1 minus 2 delta. You need both the edges to be satisfied. So that's really not a. So this one will. The soundness will remain. The completeness moves from 1 minus epsilon to 1 minus 2 epsilon. Soundness possibly is unchanged. Soundness, you can't say that this actually improves the soundness. Completeness deteriorates, but that's okay for us because epsilon was anyhow a sound. That's the first thing. The next thing which we will do, sometimes this is useful for us, we will actually make the soundness, right now the soundness, the soundness condition, to sort of strengthen soundness. To a list decoding statement. What do I mean by that? So currently we have the no cases are those instances P such that val phi is less than or equal to delta. That's called the no delta. Now what we ask is previously, right now we are asking for an assignment and saying that every assignment AB that you give to the word, sorry, there's only one assignment now. There's one assignment. What is this? Let's write this. What does this mean? That is for all colorings or labelings or assignments or colorings A from V to sigma. V to sigma, at most delta fraction edges not satisfied. Or equivalently, for every greater than delta fraction of edges, and in coloring delta fraction of edges say F, there is at least one edge in F that is violated by the coloring. There is at least one E in F that is violated by A. That's just we're saying that at most the delta fraction. So you give me anything larger than delta, there will be at least one guy that is violated. I'm going to further change this to say all these are sort of syntactic. There's nothing, all these are cosmetic changes. There's absolutely nothing That's happening. The main change will come in the next step on for every greater than delta fraction edges F and A, which is and now I'm not giving you a coloring, I'm giving you a T coloring. Every vertex I'm coloring it with a set of T colors. Hmm? Hmm? There is at least one edge UV in F such that even if there is no so U is colored with one of T colors, V is colored with one of T colors, there's not even one of these T square colors that satisfy the constraint. That is such that what I want to say is AU cross AB intersection psi UV is empty. Is that okay?
Why is this?
This is if I'm thinking of T as a constant and delta as a constant, this delta and so let's call this a nu.
It will be almost T square times delta.
Huh? So yeah, so as long as T square, so if suppose there exists one such coloring, if you choose these are all for so there I want to tell you if that is true, this what do I want to say?
Like, how can you apply at least T square?
T square nu will be delta. So delta I can choose it as small as I wanted to choose. So you give me T and nu, I will choose delta to be T square nu. So that's all that's happening here. So this is also a mere cosmetic change just because sometimes it will be convenient to come up with a list decoding statement rather than a unique decoding statement.
So we are actually T as a constant.
T will be a constant. T will be a constant. So this is also just like step 1, step 2. Step 3 is their non-trivial thing and that we are not doing. Moving from S mu will be there exists a subset V naught of V such that two percentages and the one coloring A going from U to sigma that one size of U is at least 1 minus mu times size of V 2 for all edges U comma V in U cross U A2 comma AB is V by. So previously we were saying there's a 1 minus delta epsilon fraction of edges that were satisfied. Here I'm saying there's a large fraction of vertices that every edge within it is satisfied. So creating that such a thing, and within it there is the artist is V, is U, and every edge is happy.
So here the unique element property is used.
Yeah, it's still the side UV is still a matching cluster.
In this reduction,
We still maintain matching, except the S can be, yes, the S case has been considerably strengthened. You're saying not, certainly this implies the other S case, if the graphs were regular, but they are actually going to get the stronger property.
I'm asking in this reduction, are you using the fact that this is like a ULC instance and not just a
Yeah, this is the fact it's a ULC instance. ULC instance, that's S new, so we will move. And for all U subsets of D, such that mod U is greater than or equal to mu times mod V, and P colorings A going from U to more less than or equal to P. We have that we have an edge. We have at least an edge that is violated by the D, that is an edge. UV cross this one and E intersection. That is about intersection E. Intersection U cross V. Such that AU cross AB intersection psi UV.
So the no condition is for T colorings,
For T colorings.
the yes is for one coloring.
Yeah, but that's just changing the delta to T square nu. That's the only cost of it. If T nu delta are all constants, but my choice, this is one. So this is going to be, so they modify this. This is okay, more useful to work with. So the fourth idea, the first modification is if the UGC assumption is equivalent to the following. For all mu and 0, 1, E in positive integers, there exists an R inside the vehicle set. Such that given let's given an instance of ULC is NP R distinguish if P is an S mu or P is an The main, this one about them is moving from fraction of vertices to fraction of edges to fraction of vertices. This requires fair amount of modification, and this is the first part of code again. We will, one, you will assume that this is the assumption that you're going to. Okay. And the second part of code here is the actual reduction to vertices.
This is really equivalent, it's not.
It's really equal. Certainly, this implies huge. This implies huge.
Only for regular,
Huh?
only for regular graphs.
Only for regular graphs, these only for regular graphs. So actually the first transformation which they show is you can assume that you will see that if it's true an arbitrary graph, you can make it regular. They will do that. And so the instance that they produce here will be a regular instance. Okay. This is equivalent. Therefore, in general, if taking the other UG assumption, it's better to cite quote. If you're going to state this UG assumption, cite quote and quote again. Now, we will do the reduction to vertex. So let's actually give this problem a name. Then when we form this. Yeah. New D. Fields. New D R. And where is R here? R is. That is, you tell me how small mu is, how large E is. These are two constants. That will tell you how large a label set I will choose. And I have to give you will see instances where the label set is of size at most that are. On this object. Yeah. Going to be a reduction from. Yeah. Unity on. Let's see. Vertex cover. In particular, the S case, when it's an S mu, we are going to modify. The P is going to get the reduction which we described will take an instance P and from it produce the graph to the set of vertices, the set of edges. It will be a weighted graph. So there will be response. But that in the S case,
Weighted on the.
weighted on the vertices. It's vertex. In the S case, T will have half minus alpha fractional independence. It will have at least what would that mean? That means the G has a min vertex cover of size at most half plus alpha. It was a complement. He has a vertex cover size most half plus alpha. Fraction, I'm only talking about fractions. I'm assuming the weight of all the vertices is 1. So this is comparing it to the total weight of the vertices. And in no new, we show that every independent set in with the size utmost fraction size utmost beta. That is what does that mean? That is every vertex cover of G is of size at least one minus beta. And the way this reduction will go will be alpha and beta can be made arbitrarily small if I'm allowed to choose T and nu to my choice. That is, the way it goes, we will show that for all alpha beta in 0, 1, there exists T and nu such that they are whole. And T and nu, this T and nu will then determine the R that I want. So each of them will be constants, but they will be constants which are percolating. These constants will be independent of the size of the. Okay, and because of this will tell you that you cannot get a better than a 2 approximation. Because in one case, the vertex cover is of size half plus alpha. In the other case, the vertex cover is of size 1 minus beta. Therefore, you cannot get an approximation better than 1 minus alpha plus beta. And alpha plus beta can be made as 2 minus alpha plus beta. 2 minus alpha plus beta can be made as small as possible.
It only shows independent of weighted vertex cover.
Huh?
It only shows independent.
Of weighted vertex cover, but I think you can convert weighted vertex cover into regular vertex cover by sort of discretizing levels.
As long as the weights are small and
As long as the weights are small. So the weights will all be functions of alpha, beta, T, mu.
The maximal matching is there to
2.
it also also weighted. What is the two approximation for weighted? For LP or
The LP works.
because in the optimal solution, all determinants are at most.
Yeah, the LP works. So what is the reduction? So T and nu will be constants which we'll eventually set. T and nu will be constants.
The scale is not.
Yeah.
So, yeah.
And the reduction will not be contained. Very kind ULC was like that. ULC was on vertex at B. And there was an underlying, the ULC instance was the bipartite graph, sorry, not a bipartite graph, it is the regular graph. A label set sigma and a math set of matching permutations and size of sigma was. Now I need to define G. So this thing is going to be every vertex here. We are going to do what we have been always doing. We are going to blow it up to a cloud to covers. The usual, we're putting a hypercube for every vertex. So the G is going to be E W. V is going to be V cross 2 sigma. And now what are the edges? I need to describe the edges. So I have to describe to you when am I going to put an edge UF VG. U is the vertex, original vertex here, S is a set, V is an original vertex, G is a set. When is there an edge between these two?
If is in 0 or
Huh?
if
F and G are subsets of 2%. So these edges, vertices are now of the form V cross.
not elements of
Huh?
Yeah, F and G are subsets of sigma.
F and G are subsets of sigma. F and G are subsets of sigma. So yeah. So, take U and V to be vertices in P and F sigma, FG are going to be FG are going to be subsets of sigma, and we are going to describe just the type working and I'm going to say UF is adjacent to VG if some condition is satisfied. What? Firstly, I want to look at U and V only if U and V was an original edge in the graph, in the other graph, in this graph. So firstly, UV should remain an edge in this graph. Now, what do you want to do? So we think of F as a set of labels for the vertex U, G as a set of labels for the vertex V. When do you think we should put an edge between them?
AF intersection AG, AF cross AG intersection psi UV is 1.
Yeah. So the point is that's good if you want. We want independent set. So we want the exactly other condition, that is F intersection. So what we want is the following. So what you said is basically we are looking at F cross G intersected with psi of UV. Notice we want to put in the S case.
So if we can satisfy more edges, we want a large element. That's
Yeah, if you satisfy large edges, we want a large independent set. So we don't want to make this satisfiable. We want to wire. So what I'll put this if this is empty. So if F and G don't have a, so basically I think the non-edges are the ones which are actually the ones that we care about. The edges are because we care about independent sets here. So I'm going to put these are the reasons. Is that okay? And W, for now let's define W to be this way. We will later on see we will have to modify it. U cross F W, and this going to be put 1 over side. First pick a vertex at random times 1 over 2 power R. Just putting the uniform distribution on the. Okay. So now let's at least do the completeness.
you're going to change these scripts, otherwise what's the point?
Huh?
The way the uniform, there's no point
There's no point of what?
of having that.
Yeah. We will see. So this paper is called the original. So this paper, actually, most of the reduction comes from Dinur Safra. The whole construction is Dinur Safra. It was just Koth and Rege's observation. It's non-trivial, it's a huge observation. Dinur Safra got 1.3 something. The Koth and Rege observed that their thing was to show that if you start off with a stronger starting point, that is ULC rather than label cover, you could get 2 and not 1.3. So this proof which I'm going to give is, so the original reduction is Dinur Safra. Koth and Rege's observation is the fact that you can get that 1.3 becomes 2 if you change the starting point from label cover to ULC. So the proof I'm going to give is a proof which is actually a further simplification. It's not the one in Koth Rege's paper. It's a simplification due to Johan Haskell, Sushant Deva, and myself from a few years ago. Yeah. And actually, I'm going to be following a write-up. I taught this about 5 years ago here, and Srikanth had a very nice write-up, so basically this 2-page article. And that's the write-up I'm following for this. So let's look at completeness. So let's say P is S min. Then what's the size of what's an independent set that we can come up with? So particularly if it's an S nu, that means that is there exists a U subset of V. Size of U is larger than or equal to, it's a 1 minus mu fraction of V and one coloring of the vertices here, such that for all UV in U cross U intersection P, AU AB is in phi U. That's what the completeness means. So given this, what is the independent set we will produce?
U comma S as a U is in.
Huh?
U comma S as a U.
Okay. So it is going to be U comma F, where U is in U and AU F. Notice this is there are no edges between these green objects. I is an independent set. And what's the fraction? Say what's the weight of I?
1 minus 1 of the.
Firstly, it's at least 1 minus, because you're picking only things with you, and then
Like,
huh?
1 minus 1.
Into half. So basically, in this particular guy, you're going to pick. So it's half minus into two. So we do have a very large independent set in this case. Okay, so that's just let's record it as an observation. So the plane is P belongs to
This is
Then the raises are I. Then E has an independent set. I think it's going to be doing sounds. And in fact, plainly prove with the following thing. Here it is. Which is a function of mu and epsilon. What is epsilon? What is it? With epsilon will, we're going to change the weights. Epsilon will come there, but for now, if think of there being no epsilon in positive integers, such that if P belongs to no mu P, then the independent set of G is all the maximum independent set of G or base set of G. Or alpha G independent. Right now, there is no epsilon. The epsilon will soon enter the picture because we are going to change the weight, and that weight will be a function of epsilon. But let's repeat the claim. Yeah, okay, the story behind it. We are not going to, so right now we have used the uniform distribution on the sets, that is, each set was picked with probability 1. You either put it in or put it out with probability half each. This is the unbiased distribution, the uniform distribution. We will eventually go in which we put in an element only with probability half minus epsilon. We take out an element with half plus epsilon. And you'll see why it's important to do this. The title of the paper was The Importance of Being Biased. Okay. So the proof will be by contradiction. So let's assume there is an independent set of size larger than this and see what we can do. Proof by contradiction. Assume a subset of E such that interest line is larger than E. Now, you can look at the restriction of I on each of the individual clouds. So let IV be just the restriction of I to.
That means labeling that.
So we will eventually construct a T labeling. We'll construct a T labeling. So we will first the restriction of I to cloud to the cloud U cross to the cloud V cross. Sigma, that is IV is defined to be V cross 2 sigma intersection. Now, because weight of I is at least 2 nu, the at least nu fraction of vertices V for which weight of I nu is. Let U define U to be those vertices V in B such that weight of IV is at least. But is a fraction weight within that flow. When I mean weight, I'm meaning within that flow, not in the whole. This one, it should be clear, just averaging will tell you that mod U is of size at least mu times mod. Our goal now is to find a T covering for you. Okay. So let's observe a couple of things. Let's look at a particular line. Let's look at a particular. So now let's fix a V view. And look at IV. The IV is just a collection of sets. It's an independent set. It's a collection of sets, there are no edges between. I want to say you can actually. I want to say that you can work. Let's look at any these IVs. If you had UF, well, actually, let's say any belongs to I. So, not just a particular IV. Let's just do this one. What do we know about them? What do we know when does the fact that these two exist as an edge? This one. So either it should be the case, if suppose both these vertices are in the independent set, either it must be the case that UV is not an edge, or
If UV is an edge,
then either one UV is not an edge in the original graph, or two UV is an edge and sorry, this was
The first one is UV, not UV.
first one is not ready, and F cross G intersection by UV is not empty. That's the fact that these both vertices happen to be there. But now, I want to clearly say in either case, let F prime and G prime be two supersets of F and G. Let F prime be a superset of F and G prime be a superset of G. What do you mean in either case, U F prime V G prime also satisfies this property.
Will it be subset?
Huh?
Will it be subset?
No, superset, because F cross G intersection is not empty, therefore, we put supersets, it will continue to be non-empty. So, in other words, what we can do is we can, for any set F, once we have a set, we could add all its supersets, and this will not change the nature of the thing being an independent set. So, in particular, we could assume every IV is up closed.
So in this reduction, you're only adding edges in the graph if UV are an edge. If UV happen to not be an edge in the original, you will see instance, then there are no edges.
Yeah.
What happens? So suppose that you have a ULC instance where there's a massive independent set in the graph in the instance.
They cannot be, no, because the no instance will tell you that you will always violate something.
Oh, maybe this is one of the advantages you get by working with vertices and not edges.
Because we cannot have
Because if you are only looking at fraction of edges, then it's considerable.
It can exist a massive independent set. The vertex version tells you you cannot have a massive independent set in it. All the independent sets are really tiny. Good. So each of the IVs we can upclose it. So in particular, if we had assumed that I was maximally independent, then each of the IVs are monotone sets. So if we had assumed I free, so if I is maximum, which we can because we have one, then each IV is monotone, that is up closed. Okay. Now, what are so Nikal, from what do we want to do from IV? We want to pull out a short set of coordinate labels and say these labels more or less are going to determine whether. So notice in the S case, there was one label, it was a dictator that determined what IV was. We would like to say in this case also, we can pick a short set of labels which completely determine what IV is. We would like to say, give me a monotone function, it's completely specified by a short set of coordinates. This is just plain false. There are monotone functions. In fact, the most important of them is being majority, which depends on all the coordinates. Which depends on all the coordinates, and this is a big, a huge hurdle for us that there are monotone functions like this, threshold functions in particular, which could depend on a large number of coordinates. But let's look at each of these monotone functions. So, what are there? The dictators are monotone functions, and short functions of ands and ors are monotone. Any functions of and or are monotone. And there's of course the threshold functions are also monotone. The ands and ors, the nice thing about ands and ors are they're invariably either they are like dictator, they depend on a short set of variables. If they're going to depend on a large set of variables, they become a function which is more or less constant. Therefore, you can say that it might be possibly as a function, it's an OR of several variables, but it's mostly one. Therefore, it's approximated by a function that depends on very few variables.
How to do that?
You can't do this for majority. You cannot do this for majority. There is no way to approximate it with a function that depends on a few variables. But that is because we are working on the uniform distribution. Suppose the distribution of the inputs was not 50-50-50. You picked each variable, you set it to 0 with probability half minus epsilon and 1 with probability epsilon. Majority becomes just Chernoff bounds will settle and majority will become an almost constant function.
Like half over root, half plus 1 over root and.
Yeah, at very small epsilon, you are going to flip it. You don't have to go, you're saying you don't have to make it epsilon be constant, even at this point, you're going to make. So the point, what we want to observe is, we want to make use of factors on, there exist monotone functions that depend on all variables, you're working with the uniform distribution. But if you slightly flip it, if you slightly change the bias, this monotone function no longer is actually a more or less a constant function.
But there will still be some threshold.
So for every threshold, there could be some monotone function which actually is large, depends on all the variables at that particular. So we don't know what to do. So we are going to keep the threshold initially as a variable, and then we will fight against all thresholds and then choose one, show that one of the thresholds work. So what I want to do is I'm going to change the function. We're going to change the weight to be the weight is now going to be weight function is biased weights. weight of u f. So we will use bias weights and we will use weight half minus epsilon. Notice we'll have to use weights which are around half because the completeness we still wanted to go through. So this number half should not change too much. It should be either half minus epsilon, half plus epsilon, so that this number is still like half minus alpha. So we have to choose some weight which is around half. It could be either above half or below half. We will choose something to be below half and we'll see why that also happens later on. So we're going to choose bias weights half minus epsilon by, which is basically equal to 1 by v. And it's going to be, what is it going to be? It's going to be half minus epsilon times size of f times half plus epsilon times size of r minus. Okay. So that's the bias I'm going to use. So we'll come to your question shortly. So we want to now show. So this is the bias the threshold I'm using. It might still be in the case that when I use this particular threshold, when I use this particular bias, there is a threshold function which depends on all the variables. In particular, if I use the threshold function, if half minus epsilon guys are 1, that depends on all the variables at this point of time. So what we will further do today, so we have a slide digress into. So let's change the completeness. It's going to change from this word is going to be 1 minus mu half minus epsilon. That will be some half minus alpha or something. A short digression into and the reason basically we want to do, we want to show, we want to ask when can a function be well approximated by a function which depends on very few variables. Such a function is called a punta. And we're going to ask when is a function well approximated by a function. So we want id as a function, it's a monotone function, to be well approximated by a punta. This is not cannot always be true, but let's ask when can you do such a thing? And what is known is the influence of the function is small. Then Friedgood's theorem says that you can, if an influence, I'll define what influence is shortly. Friedgood's theorem states that if the influence of a particular function is small, influence is the sum of influences of all the variables. If this is not too large, if it is smaller than logarithmic in the number of variables, then there exists a junta which depends at most exponentially on the influence that well approximates the given function. So let's, and the reason for they wanted to get a short set of coordinates. Friedgood's theorem was the one that was available for it. So let's see what Friedgood's theorem says and see whether we can apply Friedgood's theorem to our set. So for that, the reason we are going into this digression is Friedgood's theorem gives a sufficient condition for a function to be approximated by a function. Namely, low influence. And that's why we are going into this digression. We want to define what influence is.
Your approximation with respect to this product measure.
Yeah. Approximation will everything will have to depend on this product measure. So first let's define what suppose we are working with the product measure P. So the mu P tensor R. So P is a number in 0, 1, and that's the distribution we are working on. The influence IP of any function f, and f is some function on 01R to 01. How did we define influence in the Boolean setting? We picked a random variable in the usual uniform variable, picked a random variable. I don't know if we ever defined it in this. We defined it for max cut. Picked a random x, flipped a value and checked if it is this one. Now the random thing, of course, should be picked according to the mu p distribution. And flipping there, we could do it because flipping was equally likely this one. Therefore, what you want to do is not flipping. You want to ask, what's the variance when I move this particular coordinate? So this is, you pick x minus I from mu p tensor r minus 1. X minus I is everything except the ith coordinate. Then you pick xi from mu p. You ask the variance of x1, x2, xi minus 1, xi plus 1. This is the way in which you can generalize that notion. This is exactly match our previous notion of influence. And it's almost the other. So the other notion of influence would be you pick an x at random from mu p tensor R, and you ask what's the probability that f of x is not equal to f of x plus en. Essentially, you're not picking the ith coordinate here, because the ith coordinate you are looking at both these. This will be almost this one, except there will be a p into 1 minus p. That this is okay. We work with the fun. So there are textbooks which actually will work with this as the definition of influence for any p bias, but somehow that's a cleaner definition to work with. In fact, I think Nafi Linear is one of the people who defined influence, prefers this definition and doesn't like authors using the other definition. But okay. And the total influence. So this is defining influence over here. Define total influence. IP of f. It's just going to be summation time influence. First here, the following. He needs to be bounded away from the two extremes. So he say P is between 1/3 and 2/3. It's not an extremely biased function. And I tell you the approximation I want. I tell you how well I want it to be approximated. If f is a function on R variables and the total influence of f is at most some k, then there exists G depending utmost exponential in order A over delta. Variables in R, variables. Such that the probability when you pick X according to will be tensor R f of X not equal to G of X.
One get a sense of the kind of numbers we are taking.
Yeah.
So if the I of the parity function and P is the uniform.
Yeah.
Is one.
So parity function has influenced R.
So it's one with respect to each variable. So this is basically looking at how many edges.
Yeah.
You see different.
Different color and you have to weigh it by 3 into 1 minus. Yeah.
Okay, so. Okay, so influence can be as large as the number of variables.
And then this is a useless statement. Because it's just going to say that there's a junta depending on exponential and order k.
So it's only useful in case that
Log r, much smaller than log r, and how small depending on delta. So only if the thing is that small, then I can tell you that there is a function that depends on.
and a constant function has influence 0.
Constant function is influence.
So this is like a quantitative statement. That
Yes, yeah. The free good cases.
And so what is the KKL type theorem? What is KKL?
This is KKL. Free good immediately follows KKL. It is.
What does KKL say?
KKL tells you, I think, very bad at this. Tell you, I think it's max. We're going to talk about max influence of a.
The total influence is small.
Yeah, so it means the max influence is greater than equal to omega logarithm times variance. So
For every.
So for a well balanced function, suppose it's a well balanced.
In terms of variance.
In terms of variance, so.
So now you can query the most influential variable, and then you basically take the most influential variable, take that function, and we find out who the average over the unqueried variables. Then you select the remaining coordinates of the influence. This is a good approximation.
Basically, that's how it's going to follow.
So it
Qualitative is similar.
Yeah. So this one, the way the KKL theorem goes is there is a, so the proofs now go either way. You can prove it good from KKL from it good. I think so. So the KKL says that the max influence, you give me any function, the max influence is some log n by n times the total variance.
Yes, KDR will be 1 by 8 is impressive.
There's Talagram which has an improvement of this, I think, of this one. And what, so it says if the variance is reasonable, then there exists a function and very influential variable. You take it out and you keep doing this. Fill this, and I think you should get at least a form of free goods. I don't know if you get exactly this quantitative, but you'll get something. So they would like to appeal to this. But once again, notice this is not this way, they can appeal to this only if the influence is small. IV, the function that you have, all that we know, it's a monotone function. You don't have a handle that the influence is small. But monotone functions have a very other nice property. We haven't yet used the fact it's a monotone function. So the monotone functions have a nice property.
Doesn't tell about the influence.
So the influence for monotone functions happens to be the derivative of the total density of the function. So let's say what I'm stating about this. So you can talk about for monotone functions, you can talk about mu p of f, which is basically just For monotone, mu p of f is basically mu p of set of all x such that f of x equals 1. That's all I mean. It's the mass of the ones of the function. For monotone function,
So we are viewing this as a function in P, mu P of them. So we talk about, this is a number, right?
this is a number.
P.
Yeah. So f tells you which is the one set, and you are giving a mass of it based on the p bias or the bias distribution. You are talking about the mass of it. So this notice for a monotone function, this is something which changes if it's not a constant monotone function. This is going to start from 0, go all the way to 1. So this is a quantity for non-constant functions. Non-constant functions, the non-constant monotone functions. Mu p goes from 0 to 1 as p goes from 0 to 1. The function is going to start off very slow and go all the way to 1. And furthermore, what you can actually show is the derivative of this function exactly happens to be, you can write down this function, the derivative of this function exactly happens to be the influence, the total influence that we have defined. You can, it's just quantitatively, you can just do this calculation because it's attributed to Rousseau, it's called Rousseau's lemma. That d mu p of f dp, this is actually equal to ip of f p1 minus. Why is this? So we could not apply influence directly to Friedman's theorem because we could not apply Friedman's theorem directly because the influence could have been large at the threshold we care for. But I want to claim the influence cannot be large for a whole interval because influence is the derivative of a function which is at most 1. If for a whole interval of size 1 over delta, the influence is at least going to be 1 over delta, then the function is going to go jump by a factor more than 1 during in that interval.
It's like Nissan's ability.
Yeah. So basically, this tells you that even though at half minus epsilon it might be bad, there will be a number between half minus epsilon and half minus epsilon by 2. So, sir, let's take the number p which we chose to be. We chose it to be half minus epsilon. This could be a number anywhere around half. That's all we observed. So, chose it to be p anywhere between p and p plus epsilon by 2. There has to be a point between this place where the influence is at most 2 over epsilon.
But this point will be given for
This point will be different for each we will have, because each one is a different, it will be different for each one of them. So this is what we'll call the Dinmus-Safra lemma for monotone functions, which is basically a combination of Friedgut and basically says let p be some number in say 1/3, 2/3. Fix delta, the approximation factor you want to, because that's how well I want to approximate, and f is the monotone. F is the monotone function. F. Then there exists a q in p to p plus epsilon by 2, such that and the punta g depending on at most exponential in order 1 over delta epsilon variables such that probability when I pick x from mu q cancel r, f of x is not equal to g of x at most. This is just a combination of both those things. If this was one of the crucial observations that we will use this. And this was the reason for their using biased. But we still have to come to see at this point. So at this point, what we have? So we have now applying this lemma to applying above lemma to each of I V and V and U, we have that there exists QP in half minus epsilon to half minus epsilon by 2. So each of those things have a QP and there exists QP1, QP, there exists a function called FP.
So we can actually put different bias on different vertices. We can put different bias on different vertices.
No, but the weighting is done first, then the IV is determined, it all happens in, it's fine, we will put the same weight. Is a X order 1 over delta epsilon delta. Let's call this the P epsilon delta, which is the P when I pick X UQP insert on FP of X not equal to IV of X. That's it. Fair enough. That's going to be more. So basically, this that punta, whichever get here, so this is depending on some. That's why the unit depends on me depending on CV subset of one. What we are going to do is essentially what we want to now do is this is that CV is going to be our, we have to come up with a coloring, and that's going to be the coloring we are going to come up with. So the T coloring that we are going to come up with. To define T coloring as follows. T coloring that is A moving from U to sigma assigned to P. This basically maps V to the set C. Now, what do I need to show? I need to show that. What do I need to show? I need to, let's assume that this is actually a valid T coloring. That is, every edge is, for every edge, there is at least one of the T square colors, so T square pairs is this one. Suppose that were the case, then I would want to show that actually the underlying graph, the set I was not an independence. We'll get a contradiction matrix. We would like to show that for all edges, UV in U cross U intersection E, we have AU, that's it, sorry, we have CU cross CV intersection psi UV not equal to 0. So this actually is satisfied. So let's do it edge by edge and do it. So let's fix one such edge. And this will say it's not a, this will show one, this will, for contradiction, this is what we need to show. We'll complete the contradiction. So let's prove this. Okay. So this is going to be contradiction within a contradiction. So suppose I can't show this.
I thought you were going to continue the value of the game.
There's no value of the game now, no? There's just
Yeah, that no.
So what does no mean? No means that for every T coloring, there's at least one edge violated. So I'm going to produce a T coloring that does not violate any edge. What's the no case? The no case says for every T coloring, there will be at least one edge who doesn't have a satisfying assignment even among the T square possible pairs. So what we are showing here is they are giving a T coloring such that every edge is satisfied by at least one of the T square pairs. If I show this, we will be done. Huh? I will prove this. So this is, if I prove this, I'm going to prove this itself by another contradiction. Oh, that's a, so let's prove this edge by edge.
You just want to show for one is
No. I need to show this is a, so I'm not sure, I need to show this violates the no instance. I have to show that this is a T coloring. You would like to show that is A is a valid T coloring of U, and hence P is not a non-UT instance. That will complete the contradiction. Fix on such edge. U. If you with me now. So so let's assume that actually that edge does not have this one. In other words, CV intersection, CU intersection, CV intersection by UV is this one. Now there are two edges UV. So fix one such edge. What we have two edges UV. We have corresponding QU, QV, two biases. We have two functions IU and IV, and we have their approximations FU and F. And these two things, there is this permutation IU is illegal. Fix one such edge. So we are going to assume that CU cross, this is also CU cross. That's the IUV. So let's assume CU cross CV intersection phi UV is actually M. To make things this one, I'm going to just assume that psi UV is the identity permutation. That's just a reordering of the labels. So to simplify matters, to simplify presentation. Assume phi UV is the identity permutation. Right? And suppose CU cross CV intersection phi UV is M. Identity permutation. And then just to make, instead of carrying so many subscripts, I'm just going to call them two vertices. This is U1, U2, Q1, Q2, I1, I2, F1, F2, C1, C2. That's the identity commutation between them. And we have C1 intersection C2. That's what it translates to. So we look at it, these are the set of R coordinates. This is C1, this is C2. So C1 is determining F1, C2 is determining F2, and these are disjoint set of coordinates. These are disjoint set of coordinates. I want to now come and say that U1 cross, I want to now somehow come, so this is what we have at this point of time. So to complete this contradiction, it suffices to demonstrate an F1 in I1 and an F2 in I2. These are two sets. Such that U1 F1 is an edge to U2 F1. So that would show this is not an independent set. If I demonstrate an F1 and F2 in I1 and I2, such that this happens, I will be done.
Is similar to the equivalence or other.
Hmm?
Yeah, very similar in
What?
you want it one similar to you.
No, this is an edge in
Oh, okay.
edge in G.
So you wanted to show that they're common independence.
Okay. So I need to suffice to demonstrate something. Right? So so I'm going to I'm going to sample F1 and F2 in a particular distribution wise, such that, and I will show that such a thing will always have this. So I give a sampling procedure. So I show a sampling procedure to pick such an F1 and F2 such that this happens. So sample F1 and F2, which are both subsets of R, as follows. What will we do? Take every coordinate, put it into F1 with probability Q1, put it into F2 with probability Q2, and put it into neither with probability 1 minus Q1 plus Q2. So what I'm going to do, sample F1 for each I in R, or sigma in R, sigma in sigma, put sigma in F1 with probability Q1, either put sigma in F2 with probability Q2, and put it in neither probability 1 minus Q1 plus Q2. And this is where I'm going to use that Q1 and Q2 are both less than half. Therefore, this is actually a well-defined statement. That's why I needed it to be half minus something rather than half plus something. So notice by the way I have done it, the F1 and F2 I picked up are necessarily disjoint. So any F1 and F2 pair sample this way. Sample I'm putting the wrong error. Or it is joined. So in particular, there exists an edge between U1 F1 and U2 F2 in the graph. Period. That was the reason we put. Therefore, U1 F1 and U2 F2. This is an edge in the graph with probability 1.
Because as a mixed identity.
Because it's identity computation. Because if you recall how did we define the graph, the edge, we put we put the edge if this one was this is the identity computation. Therefore, this is all that we need to now show is both these points are actually members of I1 and I2. That's all we need to show.
Yes.
We need to show that all that we need to show, and we are almost there. All that we need to show are V1 comma F1 belongs rather just F1 belongs to I1 and F2 belongs to I2. That's what cause our condition. But recall C1 determined F1, small f1, C2 determined small f2, these are disjoint. And what was the mass of picking up? So let's so what that is we need to show probability F1 in I1 and F2 in I2 is non-zero. That's the probability we need to show.
Each of them is bigger than something. Bigger than half.
We don't yet know, but let's go to the condition that F1 is small f1 and F2 is small f2, which are approximations of I1 and I2. Let's ask that first. What about probability F1 in F1? So that's a function. I'm going to write that F1 of F1 is 1 and F2 of F2 is 1. But F1 and F2 are both kuntas which depend on different sets of variables. And the way we picked F1 and F2, this will show you that this actually breaks up into a product distribution. Because F1, for checking this, you need to look at certain coordinates. For checking this, you need to look at certain other coordinates. And this actually breaks up into a nice product distribution. This is a product.
Here the randomization is over.
The randomness is about the way we are picking each coordinate.
The randomization is over F1.
The randomization is over F1.
But since they're distant, then there isn't a correlation. But F1 and F2 are disjoint.
F1 and F2 are disjoint, but yet these two events are independent. I'm saying this event depends only on how I'm tossing the coins in C1. This event depends only how I'm tossing the coins in C2, and they are completely independent because C1 and C2 are disjoint. So this is just probability of since C1 intersection C2 is empty and F1 is Fi is a Ci kunta. Okay. But what is this? This is exactly the mu Q1 mass of F1. This is exactly mu Q1 mass of F1. This is the mu Q2 mass of F2. Okay, so that at least is a non-zero quantity. What we actually wanted was I1 and I2, not F1 and F2. Firstly, let's look at what are these quantities. So mu Qi of Fi is certainly greater than or equal to mu Qi of Ii minus delta. That's just the nature, that's because it's an approximation. Now, what we know about mu Qi Fi, what we know is this. This is certainly greater than mu P of Ii minus delta, where P is the original half minus epsilon we had set it, because that's only a smaller value. The mass can, for a monotone function, you reduce it, it's only this one. And this we know is,
So basically the Qi greater than P.
huh?
This is because Qi is between half and.
Wait, Qi is the number between P and P minus epsilon by 2. Qi is larger than P.
But is the mass, is the weighted mass monotone in respect to Q?
Because I is a monotone set, no? Oh, because I is a monotone set, it is going to increase. And this is E, and this is we know is red. This is mu minus delta. So each of these is at least mu minus delta. So we haven't yet decided, remember, we haven't yet chosen our approximation parameter delta. So this will tell you I have to choose delta to be at least at most mu by 2. So this is greater than mu by 2 if delta is less than mu by 2. So we have to fix our approximation parameters. There will be some more conditions coming. So at this point of time, we have managed to get hence probability over the choice of picking F1 and F2. F1 of F1 equals 1 and F2 of F2 equals 1 is at least mu square over 4.
So here the bias we are getting about the cloud of P is Q of P.
Huh?
The bias we are giving on the hypercube of V is Q of P.
No, this is very different. It's a very strange. This is the way I'm picking up F1 and F2 is very odd. The probability distribution is over F1 and F2. Where I'm picking up this coordinate by setting F1. For F1, I'm choosing it in according to the Q1 bias distribution. For F2, I'm picking it according to the Q2 bias distribution. But they are picked up in a correlated fashion such that F1 and F2 are always disjoint with each other. So they are picked and correlated, but here because F1 and F2 were puntas and disjoint sets, I will take it as a product and go. All of this is happening. It's a very clever setup of parameters, the way things are going on.
So essentially what you did there was that this event was easy to analyze for the approximation, little F1 and little F2.
Yeah.
And these are good enough approximations. So you can relate it to.
Yeah, but you haven't yet, we have to relate it. So finally we'll come to that. We have to come to I'm going to ask this distribution picking F1 and F2. It's a correlated F1 and F2. The marginal F1 is exactly mu Q1. The marginal F2 is exactly mu Q2. But they are correlated so that they are always disjoint. I want to ask what is the probability? F1 is in I1 and F2 is in I2. I want to claim this is certainly at least the probability F1 of F1 is 1 and F2 of F2 is 1.
So now they are not disjoint in.
Here
they are not disjoint in.
Which one?
In this.
So I have to tell you about it. Minus 3. 1 of F1 is 1 and I1 of F1, I1 of small f1 is not 1 minus probability F1 of F2 is 1 and I2 of F2 is not 1. So I'm looking at this event space I1, I2, the small f1, small f2.
So these two, both these events are going to be upper bounded by the distance.
The upper bounded, yes. And the first, so that's it. Basically, if you believe this inequality, this is greater than or equal to mu square by 4 minus 2 delta. Because the first event depends only on the choice of F1, and that was marginal on Q1. The second is only on Q2. The first one you already argued independent. Yeah, so if you believe that inequality, you should buy this, but that inequality should be clear. So that's if these two bad events don't happen, then those two are the same. I'm just pulling out those two bad events. And that's
So in this second term, probability F1 equal to 1 and I1 F1 not equal to 1.
yeah.
The probability is over to Q1 bias space.
Its probability is over F1 and F2. F1 this joint distribution, but the point is F2 does not even figure in it. Therefore, only the marginal distribution F1. Therefore, it's a Q1 bias space. And that's why it's the 2 delta from there. And the similar one is another delta from there.
So just one maybe one more.
Yeah.
So in the reduction,
Yeah.
the weight we are giving for the hypercube of P will be Q of P.
No, the reduction is going to give P. IQ of P is comes in the analysis. You tell me the independent, you tell me there's a large independent set, and I pick out a QV.
Okay. So the bias is P over the P bias.
The bias I choose it to be P
For every
response. I just choose it to be mu P, which is half minus epsilon. Each one of them will choose for the analysis will move to some half minus epsilon prime, which is a number lying between half minus epsilon and half minus epsilon by 2.
This QV is that for time.
That's QV is what's on here.
So maybe I want to say another point, but the P you choose when you move from unweighted vertex cover, weighted vertex cover to unweighted vertex cover.
Yeah.
Okay, depend on the denominator of P will be
Yeah, but these are all constants. These are all just constants, right? No, they're all constants here. So this is greater than or equal to mu squared by 8 if delta is smaller than mu squared by 8. That's what I want. Mu squared by 16. Yeah. So that's what we'll set delta to be. Right.
It's a nice reduction.
Huh?
It's a very nice reduction.
It's a very nice. Delta to be the square by 16. D to D. D epsilon. F1 is the right one. F2 is the right two. Minus. Yes. There are two contradictions going each other, but it's fine. Or just the.
So the ULC property was stated only because we could assume that the identity connotation.
Oh, pardon.
So why did we use the ULC property?
Yeah, we could assume it's identity property. Otherwise, I don't know how to do this proof. That's where I used. Yeah, it's a cute proof. Of course, it's got simplified. So this Dinur which is fairly important. I would like to see the simplification go into Dinur. I wanted to see do the simplification in Dinur Safra. Now, of course, it's not quite worthwhile doing it because there's a better reduction. 1.3 has been beaten. Now 1 square root 2. Then Boltregev came. Boltregev was also the reduction is more complicated. Then this is what Sushant, Johan, and I had. And by the way, so Srikanth further simplified the proof while writing it up. So this current proof is a product of all of these things. This actually, I think it's a fairly elegant proof given what we have. And Dinur Safra, their biggest contribution in some sense was the use of till Dinur Safra, external combinatorics were not being used for hardness reductions, and they sort of said that. And they use it in a very clean and very straightforward. There's nothing magical going on over here.
So the proof of this, there are two parts of this, right? The derivative relation is exactly Nissan's negative, or is this?
Which one? This one? You did
In the proof of, yeah, in the proof of Dilip Safra, you're going to rely on the fact that MUP is not going to be, sorry, IP is not going to be large for,
Yeah, but that just follows because it's a derivative.
but the fact that derivative of bounded function cannot be,
If it is bounded function has a derivative 1 over epsilon for a range or 2 over epsilon for an entire.
so I, oh,
No, this is
all, that's all you.
That's all I'm asking. So bounded function cannot have a function that's between 0 and 1 cannot have derivative 2 over epsilon for an entire interval of.
That's all.
Yeah. That's all I'm saying. It's just that. So this is actually a straightforward corollary of the two of Friedwood's lemma and Rousseau's lemma. I just that call it a lemma because it's used now. It's been used multiple times. It's a good fact to keep in mind that these monotone functions many a time are problematic for us because they can influence a large number of variables. But if you slightly change the bias, you just kill that. And that's basically what's happening. But that is, they will all monotone functions. Essentially, this is stating will become juntas if you slightly wiggle if you have a little wiggle room around the bias. And that's their main, that's the Safra's main observation. And then the proof goes to. Of course, their proof is far more involved than this because they don't have it to be a permutation. So they have to do lots more work to build. Co-threaded, and this proof becomes simpler because it's a permutation.
So basically, the starting assumption was not ULC, but the
Starting assumption was not ULC, but there's a complicated assumption based starting with label cover that they use, which is there. Yeah, but essentially, this is the heart of this is their starting point. The paper was called because of this, the importance of being biased. And no, I think it's a. But since it's paper now, XML commentary results also have been used a lot and say. Okay, so it's 12. So we can do one of two things. Okay. So we come back to part 2 of today's lecture. So we'll start starting a new topic. We'll revisit the low degree test and see whether it can prove a stronger low degree test to construct a PCP theorem, rather PCP theorem, and actually hardness of gap label cover, which bypasses an application of the parallel application theorem. So into PCP constructions. In particular, PCPs with very low soundness error. Bypassing the use of parameters. Yes. And basically, how we are going to prove this is we are going to appeal to so how did we prove the PCP theorem? The workhorse behind the PCP theorem was the low degree test. That was this one. And we gave the Friedel-Sutton analysis of low degree test, which was then converted, which we then used by arithmetizing the SAT problem to construct a PCP theorem. Now, what we're going to ask is if we had even stronger analysis of the low degree test, can we construct an even better PCP theorem from it? The reason why did we have to apply parallel? So we recall how things were. We first proved PCP theorem. This was using the low degree test. So this gave gap 1 versus say 0.99 label cover hardness. That's what it gives. Then we apply parallel repetition theorem. Which then posted this, we have one delta label cover hardness. This was just a fixed polynomial time reduction from SAT to this. This reduction took time n to the power order log 1 over delta. And if you recall, several of our so if you recall, when you wanted to max pre-learn, we include 1 minus epsilon versus half plus epsilon. That epsilon, how small we wanted to that epsilon, the smaller we wanted that epsilon, that would make this delta smaller. So in particular, that epsilon would never be made sub-constant, because that would imply that this delta had to be sub-constant, which would mean the reduction has to run on super polynomial time. And there were some problems for which we did need sub-constant hardness of gap label cover. In particular, set cover was one such problem for which even for set cover there's a very natural approximation algorithm which gets a ln n approximation. This is the greedy thing which gives you ln n. You can show actually it's ln n and the constant before ln n is 1. That's the approximation. That's why it's called ln n and not log n. What is the constant is it's log n to the base e. That's the approximation. We wanted to get optimal hardness for this. So Pege showed that if you assume that gap 1 over log n label cover was hard, he could do it. So this problem. So in particular, if his reduction for that case required, so the question is, can we obtain yeah, 1 delta LC hardness for delta being little over 1. In particular, an application of this was due to result to Fege, where he gave a reduction from gap 1 over log n LC to ln n into 1 minus epsilon approximation for set cover. So one way to obtain this result was actually to get delta to be log n.
Shouldn't epsilon somewhere come in the first?
Huh?
Shouldn't epsilon somewhere in the first?
It will appear in the order 1 over log n. So it's not a 1 over log n, but the constant before the log n. What? So you could, so in particular Fege's reduction at that point of time when Fege wrote it, he said there's a set cover does not have a ln n approximation unless NP is contained in n to the power log n, which is what you would get if you had done the root experiment. Question is, if we can show gap label cover 1 over log n is hard using just regular polynomial time reduction, this is a reduction which will collapse to n. The reduction will only require NP not equal to, not NP not in d time n to the power log n. So there are some, so that's an application for which we really require delta to be sub-constant. So this is a question which we are going to ask. And also even just that's a place with the hardness assumption, right? Even with other reductions which you have seen already, like max 3 ln or max 3 sat, if you are able to prove it to some sub-constant delta, that will improve the epsilon to which you can show the hardness results correspondingly. Question is, how small an epsilon can you get such that max 3 ln 1 minus epsilon versus half plus epsilon is hard to approximate. Can the epsilon be made? You know it cannot be made smaller than 1 over n because there exists algorithms that get convoluted. What's the smallest you can get? And you can ask this question. So our goal is to now see if we really need the parallel repetition to do it, or can we sort of somehow soup up the low degree test so that the label cover hardness that we obtain already is very good to begin with. So there are two potential ways to do this thing. One is to de-randomize the parallel repetition. Show that the parallel repetition doesn't run in time n to the order log 1 over delta. There are two approaches. There are two potential approaches for this.
So using expander or is it?
1 second. So that's the two potential approaches. One is improve LDT to get PCPs with very low soundness error directly bypassing parallel repetition. That's the approach we will be following. The other approach is sort of whatever this means. So right now, why does the n to the power 1 over log 1 over delta comes? Because if you want to reduce the error from some constant to 1 over 2 to the k, you have to run k repetitions of the game. And k repetitions of the game makes the game go from n to the n to the power k. So possibly de-randomized So possibly you don't have to take k independent points, possibly k, not k independent repetition, possibly takes smaller number of repetitions. You can conceivably do this, but right now we don't know of any way of doing this. In fact, there seems to be Peggy and Gideon, as I say. Peggy has a lot of work in this direction. Peggy and Gideon have strong negative results in this direction. They show actually, they give, in fact, it's negative, it's extremely strong negative results. They show that for any game that you give, if the game originally itself did not have it could be that the game had an exponentially hardness score inside it. It was already a gap 1 delta level car. You just pretended it was a gap 1.9 level car hardness, and then you were amplifying. The game was not originally hard. It had there is the way one way word every half, if you choose any half the number of edges, you could perfectly satisfy it. That's what it means, that there's not a hard core. Suppose the game had this property, then what they show is whichever, if you repeat it, if you show me any set of repetitions, the de-randomized, randomized, even sequential, which achieves error better than 1 over poly k, they show you give me any way of doing the repetition, sequential, random, de-randomized, anywhere, in which the number of repetitions are less than, significantly less than k, because little o k. Then they gave a strategy for the provers which will win with probability 1 over poly k. In other words, you can never reduce the parallel repetition value by go to inverse exponential. You'll only go at best inverse polynomial. And they showed this for every single game. They showed this for every single game. They showed that basically if you use anything less than completely independent random bits, you cannot go. You cannot get values lesser than 1 over poly k. So in that sense, it's a strong. But okay, 1 over poly k is also okay for us sometimes. With 1 over poly k, we did not know how to do. And then these negative results say that we don't know how to de-randomize a parallel repetition here. It will be good if we can de-randomize it. But the failure from the negative result, basically they rule out inverse exponential decay. They rule out inverse exponential decay. They don't rule out inverse polynomial decay. You could repeat in a de-randomized fashion k times and get inverse polynomial decay. That also suffices for some of our applications. You could ask that if that would get. They don't rule out, and subsequent to the way the thing goes is the one was achieved. So the way the history goes is one was achieved by two PCPs called constructed from Ras Safram and Aurora Sudan. They gave improved low degree test analysis. Both these LDT analysis, Ras Safram and Aurora Sudan gave. So one is about one was achieved by sequence of steps. One, Ras Safran and Aurora Sudan gave improved low degree test analysis, which is the low degree test that we'll use now, not the Fred and Sudan analysis. But problem with this was it gave alphabet size. The PCP that constructed out of this had too large an alphabet size. It had very good soundness, but it had too large an alphabet size, and we had to reduce the alphabet down to a size that was manageable. So that was done by basically it was an alphabet reduction technique. The A was achieved in two processes, steps, which was first shown by Moshowitz and Ross. Moshowitz and Ross gave a specific alphabet reduction technique for the PCP constructed from Ras and Safra. What we'll see is we'll see a slightly more general technique due to myself and Giri. So the path we will see is basically we will show how to improve the low degree test analysis into Ras Safra and then apply alphabet reduction using a composition theorem suggestion, using a new composition theorem. That's the way we know how to handle one. Now two you could ask, can we get inverse polynomial error? Inverse polynomial de-randomized parameterization. And this is actually still open. It might be true that every game has a de-randomized inverse polynomial parameterization.
But de-randomized means the algorithm size.
You don't use K independent. The question queries are somehow the K rounds are not independent. You use lesser random. Alphabet growing is not an issue. It's the size of the game. Alphabet growing with order K is fine by me. It's the game size should not be, the number of randomness should not be K times log n. That's what is called killing the. So alphabet becoming order K is fine by me. I will use alphabet order K. That's okay. It's just that the number of randomness that we invest in doing K round should not be K times log n. If you do that, K can't be super constant.
So we will not try expander.
It just doesn't work. Pegakilian shows in a very strong fashion that those things don't work. Even for inverse polynomial. Inverse polynomial, I don't know. So inverse polynomial, so this is currently open. So what was shown? So this is open in the full generality. So right now I'm going to ask, if you give me an arbitrary game and you want to get inverse poly, you want to repeat it K times so that the soundness level goes down from constant to 1 over poly K. And the randomness you use is not K log n, but order K plus log n. That is K and log n get separated. It's not multiplicative. We don't know how to do this for arbitrary games. What Dinur and Meyer showed is they can do this. For what are called linear games. What are linear games? Linear games are games with special structure in which the game is a bipartite graph. Now let's associate the vertices with the vectors. Associate both the vertices, both the sides with a vector space each. This can be arbitrary. I'm just doing an arbitrary mapping. If there exists such an association, so the edges. So this is the vertex. This is the vector space V. This is a vector space W is there. So the edges are some subsets of V cross W. If it so happens the edges happen to be a subspace of V cross W, then they know how, then they could do this. If the games had the structure, that is, if the questions and the pairs of questions could have a subspace structure to them, then Zinur Meyer showed you can get inverse polynomial error. But it's unclear that the PCP theorem that comes out of the label card that comes out of PCP theorem has the structure. It could be an arbitrary thing. So while trying to get the structure, Zinur Meyer, so the way Zinur Meyer proves, they blow up alphabet to get linear structure. They blow up the alphabet a lot to get this linear structure. So in that sense, it's not a fully satisfactory answer. They take a game, they massage it to get the linear structure, alphabet becomes very large, and then they are able to get this. But now you have to reduce the alphabet again. But you luckily by then you had B with us. So then they apply B, the alphabet reduction technique of the alphabet reduction technique from there, and to get so then apply B. So their steps went in three parts once again. One. Apply. Alphabet reduction. Okay. And this is how we know the two different ways in which to get gap 1 delta label cover for inverse for delta being constant. These are the two routes we currently know. And both of them happen to use the alphabet reduction technique. It will be good to actually get a proof of parallel repetition theorem which bypasses, for which you can do it for any game, not necessarily for linear games. That will bypass the application of one. So what we will do in class is we will give an improved analysis of the low degree test using RAS, and then we'll see alphabet reduction technique. So that's the route we will take for the next 1.5 lectures.
So is the same low degree test as
Yeah. So what is the low degree test? So let's now go to low degree test.
so you're improving the softness of the composed PCP or just the outer PCP?
Which is the composed PCP.
That is the outer PCP composed with the BLR distinct PCP.
With the sound, notice that composition only deteriorated soundness. Therefore, you have to improve the soundness of the outer guy. The only place where I actually improved soundness was parallel repetition here. Every other operation that we did actually deteriorated soundness. So if you want things with very good soundness and you're not using parallel repetition, the very outer guy itself should be extremely good. What was it? So there was a finite field there. And as a dimension. E is a degree. The test was basically this. You had F was given as a table this way. In addition to that, for every line L, we had what's called on the set of all lines. You were given these.
This was not actually part of the PCP. It's lines to RSP was not actually part of the PCP.
What I'm not considering right now all the low degree test. See the low degree test, then we see how to build PCPs out of this. Let's forget about PCPs now. Let's talk about low degree test. And let's try to see what I can say about low degree test, given this, and the LED which had access to FNDA, the thing which we defined it for next is the access. He possesses pick X at random from F to M, pick L at random and lines, partition and lines containing X. Query F on X and E on L. And what's the F of X equals E L of X. And what did we use? We used the following theorem to theorem and so on. With origin minus n. For all epsilon video one. So epsilon video one, we have for magnetic field. And D such that D is significantly smaller than D is so that F is larger than there exists a universal constant C so that if F is larger than max of C times D and some order 1 over epsilon square. Then for all then the following things. For all F for all F and A, probability that F A passes will be when D is greater than or equal to 1 minus delta for some delta being less than 1 by 8 times epsilon implies that the distance of F from MB was less than 4 delta. If the test passes with high enough probability, then the function F is close to a global low degree polynomial. This is what we have. What we are now going to ask is, suppose what we are now going to ask is, suppose the probability of the test passing was not 1 minus delta, but only delta. It was a number small. Can you still say some structure? So this tells that the test passes with say 99% probability. Then you could say that there's some structure, that is the function has a good correlation with a low degree polynomial. Now what they want to ask is, you want to ask in the other end of the regime, you want to ask what if probability entity accepts is greater than delta. Can we still say, so let's to differentiate this delta from this one, let's call this epsilon. Can we still say that the problem can we still conclude that there exists a polynomial P in PMB such that the agreement of F with P is at least epsilon n for some epsilon prime, which is a function of M, D, F, and epsilon. We'll come up with what's the right definite. Can you still say this? And this is the nature of the low degree test we want. You want even if the acceptance probability is so low, you still want to say there has to be some structure. Fidelity doesn't analyze. Fidelity says the acceptance probability is 99%, then they say there's some structure you can see in the points table. But what is acceptance probability so low? Can you expect? So, and this is a sort of other. So Aurora Susan exactly did this. Aurora Susan told the following theorem. They show that there exists an epsilon naught that is for all fields F dimension M degree D, there exists epsilon naught, which is M times poly T and 1 over F, such that I write it in a very succinct format, so that the agreement, expected agreement over lines of F restricted to lines with P1D. Notice this is exactly the probability of the test passing, the low degree test passing. If this is at least epsilon, then the agreement of F with PMB is greater than epsilon minus. So Aurora Sudan proved this. Okay. So this is a sort of theorem we would like to. We'll then have to show how we can construct a PCP out of this theorem. But actually, this theorem we don't have the proof is more involved. So almost parallel to the work of Aurora Sudan, Ras Sabra considered a slightly different test, in which the only difference was Ras Sabra considered a variant of the low degree test, variant of the lines point LDT. And what they chose, this is choosing a random line. This is the plane point test. The random line, they replaced it with the random plane. And they were able to get a cleaner analysis for this. Right now it's Aurora Sudan and cleaner, and also like the parameters are better. So let me write the Ras Sabra statement. The Ras Sabra theorem. This is the following. Okay, this is very similar to above, for one fields F, dimension n, degree D. There exists epsilon naught equals n times poly in D over F. So this will come to quite slightly different from quite different, such that agreement, now expected agreement, I'll choose a plane. S. It's P, 2, P is greater than equal to epsilon implies agreement. The dimension has to be at least 3 for this. Dimension at least 3. Okay. So there's a quick comparison between
What, which candidate improve?
let's see, between Aurora Sudan plus firstly, this was a 9 point, and this is a plane point. In that sense, these guys are, this is uses lesser randomness than one. Two, the epsilon naught in Aurora in this one was m times poly p 1 over size of f. The loss you get, whereas here it was epsilon naught m times poly in the fraction d over f. So this said that, and you should actually look at the polynomial what happens. This says that it's sufficient for f to be a large constant times the degree. Whereas this one will say f has to be some polynomially larger than the degree. And that sort of gives you that. Notice f to degree d is affects the rate of the code. So this gave you actually better rate than this object. So in that sense,
So here in the poly, the exponent of D is larger than the exponent of
the exponent of d is larger than the exponent of. Notice firstly, exponent of f has to be large. D over f, there will be a Schwarzschild error that will come in most of these groups. So f exponent in f will always be is larger than this one. Here you're going to get a much larger. In that sense, Rasafra was, and it's open if Aurora Sudan you can achieve this parameter. And the other difference is Aurora Sudan is a fully algebraic proof. This is a combinatorial proof. I'm not going to go with which is better over here. Yeah, so different people have different states over here. So what we will see in the next lecture is we'll see Rasa first. To a large part. I might not be as detailed as I've been in the previous. So far, every group I've done it in every single detail. This won't be, we won't be doing it for Rasa. And with the high level ideas, which more or less we convince the theorems. That's what we do Rasafra. Once we have Rasafra, I'll sort of show why the Rasafra statement implies a corresponding PCP theorem. The same way we got, so this will be the outermost PCP. The alphabet size will be too large, then you'll have to do composition. This will be a different composition from what we had done in the past. We'll do that composition. So we have to do all these 3 steps to finish the gap 1 delta label coordinates for delta being sub constant. Let's start.